Okay, so an inverse of a matrix. Inverse of a matrix. So again, they mention how matrix algebra can provide tools for manipulating matrix equations and creating formulas. This section investigates the matrix analog of a reciprocal or multiplicative inverse. So you've heard of inverses before, like for instance, the multiplicative inverse of a number, okay, like the multiplicative inverse of the number 5 would be 1/5, because, or which we can write as 5 to the negative first power. 5 to the negative first power times 5 equals 1, and 5 times 5 to the negative first power also equals 1. It requires, an inverse requires both equations. Okay, you need both ways to work. All right, and a matrix A, if we go to talk about an invertible matrix A would be one where C times A equals the identity and A times C equals the identity. That's an invertible, so that matrix A would be invertible. And I is your identity matrix. Okay, so in fact, the inverse matrix, A inverse, we denoted A to the negative first power, but it doesn't mean we can't take a matrix and raise it to the negative first power. It's just notation. The unique inverse is denoted by A to the negative first. So A inverse times A equals the identity, and A times A inverse equals the identity. Okay, and the thing is, not every matrix is invertible. And when we talk about invertible matrices, we're talking about square matrices, matrices that have the same number of rows and the same number of columns. Okay, that's what we talk about. If an invertible matrix would be a square matrix. Okay, but not all square matrices are invertible. A matrix A that's not invertible is what we call a singular matrix. Okay, and an invertible matrix is called a non-singular matrix. All right, so a non-invertible matrix is singular, but an invertible matrix is non-singular. Okay, non-singular. So for instance, in example 1, they give two matrices A and C, and A times C, if you do the row column rule for multiplying the matrices, like for instance, how do we get a 1 here? All right, well, if we take the first row of the matrix A and the first column of the matrix C, 2 times -7 plus 5 times 3 equals 1. Okay, cool. On the other hand, this 0 here, if we take, that 0's in the second row and first column of the product matrix A times C. So if you take the second row of A, -3, -7, and multiply it by the first column of C, okay, you will hold on, let me get that thing off. You will get -3 times -7 plus -7 times 3 and get 0. And the point is, when you do all the operations, you get the identity matrix. But in order to verify that C is the identity, in order to verify that C is the inverse of the matrix A, that means that C times A also has to equal the identity matrix. Okay? So that's how so it's analogous, showing that a matrix A is the inverse of another matrix is analogous to showing that a number is the inverse of another number. Okay, it's analogous. And And there's a formula, a simple formula for the inverse of a 2 by 2 matrix. Okay, if you have a 2 by 2 matrix, the inverse of the matrix is given by this formula. Okay, and that can be proven, but we won't worry about proving it right now. But how many maybe have seen that formula in another class for the inverse of a 2 by 2 matrix? Sometimes students see it in other classes. Okay, Benjamin's seen it before. Okay, Catherine and Abby have, and Francesca and Kayla. Very good. All right, Samantha, I mean. All right, very good, very good. So okay. Well, the denominator here, okay, the denominator A times D times minus B times C is the determinant of this matrix A. Okay, that's called a determinant. And how many maybe have seen a 2 by 2, a determinant for a 2 by 2 matrix before, like that? It's usually pretty common for students to see that, but doesn't mean you've had seen it. Okay, Elaine's seen it, and Nafani and Catherine. Okay, very good, very good. So if the determinant equals 0, then A is not invertible. Now, why would that be? If the determinant here equals 0, then the matrix A doesn't have an inverse. Why is that? Based on the inverse formula. Why would that be the case? Good, good, good. You can't take 1 and divide it by 0. So in the formula, you have 1 over the determinant of A. And if that determinant of A equals 0, you have an undefined situation. Okay, are there any questions on this? Okay, all right. Well, so of course, there's, they outline the proof in 2 of the exercises in the book, but here's an example where they have a matrix A and they find its inverse, and really it's just applying the formula. It's not a big deal. It's not a big deal to do that. Okay. All right. So they mentioned that invertible matrices are indispensable in linear algebra, mainly for algebraic calculations and formula derivations, as in the next theorem. Well, here's a theorem. Now, here's a theorem that's really very nice to have. Theorem 5. If you have an invertible matrix, then the matrix equation A times X equals B is going to have a unique solution. X will equal A inverse times B. Okay, that's an interesting formula. Okay, so let me show you. Let me show you why it's true. Let me go to the whiteboard here, and let's see here. So let's say you have A, and we're saying A is a square matrix. Okay, so you have A times x. X is a vector, an n by 1 vector. The matrix multiplication is defined because you're taking A, the number, the column number in the matrix A equals the number of rows in the vector X. I mean, the vector X is a matrix, right? It's just a n by 1 matrix. So in this scenario, the matrix multiplication is defined, and it's going to equal, let's say it equals the vector B. What are the dimensions on the vector B, by the way? What would the dimensions be on the vector B? It's going to be an n by 1. Good, Nafani. An n by 1. And by the way, now let's suppose also that A, hold on here, I got some cook here to get off. Okay, let's suppose that A is non-singular. Non-singular. Well, what does that mean if the matrix A is non-singular? What's that tell you about the matrix, this square matrix A? What does it have? What does this square matrix A have if the matrix A is non-singular? Good, Benjamin. Matrix A has an inverse. That's right, Nafani. It has an inverse. So here's what we're going to do. We can take this system of equations represented by this matrix equation, and what we can do is we can multiply on the left side of A times X, I can multiply by A inverse. Now, would it be okay to multiply the right side by A inverse like this? Would that be all right? Or should the A inverse, okay, Lewis says no. Why is that? Why is this not allowed? That's right. Lewis says you'd have an n by 1 vector times an n by n vector. So over here, the matrix on the right side here, the matrix, the matrix multiplication is not even defined. So A inverse has to be over here. But there's another reason. Well, yeah, that's right. Let's just go with that. Let's go with that. That's fine. So, okay. All right. Now, is it okay? So really what we have here on the left is we have A inverse times A times X equals A inverse times B. Is it okay on the left side to rewrite the left side as A inverse times A times a vector X equals A inverse times B. Can I rewrite the left-hand side of this matrix equation as I show you here? Is that okay to do? It is. Thank you, Nafani. It is. Because from section 2.1, we learned that matrix multiplication is associative. So we can like here on the first step here, I'm associating the matrix A with the vector X. But on the second step, I'm associating the matrix A with A inverse. So it's okay to do this. It's okay to do this. We haven't violated any matrix laws. And I want to do that because let me ask you, what is A inverse times A equal to? That's the identity matrix. Good. Good, Lewis. Good, Nafani. That's the identity matrix. So that's going to be I sub n. So now I have I sub n times the vector x equals A inverse times the vector b, right? Well, what is the identity matrix times the vector x? What is it equal to? X. That's right. Good. So x is equal to A inverse times the vector b. And so now we have a solution. We have a formula for finding the solution vector x. Now I'll comment, you're not allowed to use this formula on the exam 1, okay? Because exam 1 covers sections 1.1 to 1.8, and you didn't learn this technique in any of those sections, okay? So this is a beautiful thing you just learned, but you can't use it on your first exam. If you're going to solve a system of equations, you have to use row operations, okay? This formula comes from chapter 2, and that's not on the first exam, right? Just so, you know, like you kind of see this identity, you know, if you have like 1, 0 times 0, 1, okay, and you were to multiply like 3, 2, okay. Do you see that how I'm doing the row column rule? What I'm trying to do is I'm trying to show you just, you know, why the identity times a matrix or vector will give you the matrix or vector back. I'm trying to help you feel comfortable with that. Okay, so I'm kind of moving quickly here. Actually, I have space. I didn't need to. So I'm doing the matrix multiplication. I don't know why that's not doing curvy. I want curve. Okay, so I'm just checking here. Okay, we're gonna get then 3, 2. So I just wanted you to see the identity matrix, you know, in action once, multiplying something, so you can see why they call it the identity matrix. It's like for number multiplication, 1 is the identity. 1 times any number is the number. You know, 1 times 6 is 6. 6 times 1 is 6. You know, and so forth. Okay, are there any questions on that? All right, if there are no questions, I'll go back to the textbook. Okay, well, let me go back to the book here. One moment, I have to, let me see here, I gotta, one moment, class. Wait, validate. Yep, hold on. Okay, all right, let's go back to the book here. Okay, so they give an example about how an inverse can be used to study a horizontal elastic beam. If D is what's called a flexibility matrix, its inverse is a stiffness matrix. I'll let you look at example 3, okay? But that's an engineering application, okay, where beam has deflection. Let's continue here. So, okay, example 4. Okay, here you have a system of equations. And the matrix A in example 4 is going to be 3, 4, 5, and 6. It's a 2 by 2 matrix with first row 3 and 4, second row 5 and 6, and then the vector B is 3 and 7. So here's X equals A inverse times B, and you get the answer. Okay. There's theorems regarding inverses. If you have the inverse of an inverse, that equals the matrix. If you have the inverse of a product, A times B, where A and B are invertible matrices, square invertible matrices, the inverse of the matrix product A times B is equal to B inverse times A inverse. And then finally, if you have the inverse of transpose matrix, that's the same as the transpose of the inverse matrix. Okay, are there any questions so far? All right. Well, we've been doing all right. We've been, you know, how many are so far feeling reasonably comfortable with section 2.2? Maybe give a few thumbs up if you're okay. Okay, Benjamin's good, Samantha's good, Nafani's good. Excellent, excellent. Catherine's good, thank you. All right, thank you, Lewis. And you know, we can find the inverse for a 2 by 2 matrix. We have a formula. What if we wanted to find the inverse of a 3 by 3 matrix or a 4 by 4 matrix? How would we find the inverse for a larger square matrix? I mean, we we need some algorithm to do that, right? We need some algorithm to do that. Well, there is an algorithm for finding the inverse of a matrix, and you can use this algorithm for a matrix of any size. So let me go down a little bit here. Let me keep going here. Okay, an algorithm for finding A inverse. And I'll theoretically justify this algorithm. But first, let me just show you the algorithm. So, all right, what you do is you create a matrix where the matrix has matrix A and the identity matrix in it. And if the matrix A is row equivalent to the identity matrix, okay, then the matrix with the A and the I in it is row equivalent to the matrix with the identity and the inverse. Row equivalent, saying the matrix A is row equivalent to the identity, that means you can do row operations to reduce the matrix to the identity. In other words, if you get the matrix A in reduced echelon form, it's going to be row equivalent to the identity matrix. Now, we're not talking an augmented matrix here, we're talking just a matrix. Okay, so they're not saying the matrix A equals the identity in this algorithm. They're saying the matrix A is row equivalent to the identity. So if the matrix A is row equivalent to the identity, that means you do row operations on the matrix A, and it reduces the matrix A to the identity when you get it in reduced echelon form. So let's look at an example here. Let's look at an example. Okay, so here they want you to find the inverse of this matrix A, this 3 by 3 matrix A, if it exists. Okay, so what they do is they put the matrix A, and they create well, let me ask you this. The matrix A, what's the size of the matrix A? What are the dimensions of the matrix A? Okay, good. It's a 3 by 3 matrix. What would the corresponding identity matrix be? What would the size for the identity matrix be? If the matrix A is a 3 by 3 matrix, then the identity matrix would have to be what size would it have to be? Use your intuition. So if we're working with a 3 by 3 matrix A, then if we could reduce that matrix A to the identity matrix, what would the size of the identity matrix be? 3 by 3 also. Very good. Very good. Good hum. Good lady. So what they're doing here in the example is they're saying, let's create a new matrix that contains the matrix A and the identity matrix. And that's what they have here. Big matrix that has the matrix A and the identity. Okay, so far so good. Are there any questions so far here? All right, all right. Let me just see one thing here. So, okay, we're fine. So hold on. So what do they do here? Okay, this 3x6 matrix they're saying is row equivalent. Well, they're actually, hold on now. Yeah, they're actually going from left to right. I think it's better to always work downward when you're doing your row operations, but they're trying to save a little paper. So what they do, let's look at this here. What did they do? What row operation did they do on the matrix A? Okay, so hold on. I have an idea. And I kind of like doing it this way, you know. Hold on, I have an idea here. Here's the matrix A. And they did a row operation. Okay, row equivalent. That's what this symbol means, row equivalent. What row operation did they do on the matrix A? So row operations can be interchanging rows. You can multiply a row by a number and add it to another row. You can, let me see. Hold on, there was a chat comment here. Yes, that's right, Nafani. They interchanged rows 1 and 3. Okay, they interchanged, wait, no, I'm sorry, they interchanged, man, hold on here. They interchanged rows 1 and 2. Thank you, 1 and 2. All right, very good. So far, so good? Okay, well, now what do they do with the identity matrix? What do they do with the identity matrix? What do they do with rows 1 and 2 of the identity matrix? So the matrix A, they interchange rows 1 and 2. The identity matrix, what did they do with rows 1 and 2? They interchange them as well, because you're treating this like one big matrix. So if so essentially the row operations that you're doing on the matrix A, you're simultaneously doing those row operations on the identity matrix. Okay. All right, well, hold on here. I want to just, please let me know if you have any questions. If you have any questions, please let me know. Man. Keeps messing up here. Hold on. Why can't I get that off? It must be double colored or something. Hold on. We'll get it. Okay, now we get down to here. All right, and here is the row equivalent form of matrix A. What did they do? What did they do? So this was matrix. Hold on here one moment. Gosh darn it. Don't do that to me. One moment. I'll just do it piece by piece. Sometimes That's what you got to do. So what did they do here now in this new step here? What did they do to matrix A? What was the row operation they did? Peter? Okay, wait. Abby says they took 3 times row 2. Hold on, one moment, class, one moment. Let me just get this yellow off here. I just want to be sure you're focused. This will be good for the recording, right? Let's see, 3 times row 2 plus row 3. They're doing something where they're taking a multiple of a row and adding it to row 3. But what are they doing? I appreciate all the participation. Okay, that's right. They're taking -4 times row 1. That's right, Hung, and adding it to row 3. Abby, do you see that all right? Are you comfortable with that? Okay, good. But now, okay, I think I see what you were doing, Abby. You were going downward. Yeah, I know. They're trying to save paper. They're going from left to right. I would appreciate it in your work for the exam if you just work downward when you do your row operations and not go like sideways. It's confusing. But now what Abby said is correct. Now when you go from this, to this next matrix A, well, hold on. Before I do that, do you see now the identity matrix? They're also, for the identity matrix, taking -4 times that first row and adding it to the third row. And that's how you get negative, you get 0, -4, 1. And they keep doing this. What they're trying to do is they're trying to get that matrix A in reduced echelon form. So next thing they want to do is they want to get a 0 where that -3 is. So they take 3 times row 2 and add, well, they take 3 times row 2 and add to row 3. And I know it's getting out of control, the coloring, but do you see how the row, I mean, just what they're doing is they're getting the matrix A eventually in reduced echelon form, and that's how you get the identity down here. The matrix A reduces to this identity matrix, but they're doing the equivalent row operations on the identity matrix on the right. And what happens is when the matrix A is in reduced echelon form, that means that because it's invertible, it becomes, the matrix A gets row reduced to the identity. Then the matrix I on the right, the identity matrix on the right gets row reduced to become the inverse matrix. And then that's your inverse matrix. That's your inverse matrix. Okay, and that's how the algorithm works. That's how the algorithm works. And you can check your final answer. You can check your final answer there to make sure A times A inverse is the identity. I mean, are there any questions on this on this example 7, where we're finding the inverse. Is anybody? I mean, basically that's how it works. But is anybody confused about what's going on? I mean, does anybody need a little? Do I need to talk a little bit more about the process? All right, who's reasonably comfortable with this process? Okay, Abby's okay, comfortable. Samantha, good. This process, Benjamin's comfortable, and Ariana and Nafani, excellent, excellent. And normally, like for the homework, I mean, of course, if you had a 4x4 matrix or 5x5 matrix and it were like a dense matrix, meaning it didn't have a lot of zeros in it, it would take a while to reduce the matrix to find the inverse. And I remember when I took linear algebra in college, I had to find on an in-class exam, I had to find the inverse for a 4x4 matrix, and it can get complicated because you get fractions, but you'll be happy to know I got that problem right. I got that problem right. But when I did the problem, I had they had these little like test booklets. How many have seen these little test booklets? Where like maybe you take an in-class test and you have a little test booklet. I don't know if they use those anymore, but Justin knows what I'm talking about. Okay, yeah, it's like half the size of a piece of paper basically. And anyway, this 4x4, the blue ones, that's right. And this 4x4 inverse, I was spending, I probably used a third of that book or half of the book doing the work, because, but at any rate, okay. So the point is that the row operations that you do to reduce the matrix A to the identity matrix are the same row operations that will convert the identity matrix into the inverse matrix, and that's how you find the inverse. Okay, that's how you find the inverse. And they talk about, I mean, that's the algorithm, and then they formally represent it as a theorem, theorem 7. Any square matrix, and a square matrix is invertible if and only if A is row equivalent to the identity. And in this case, any sequence of elementary row operations that reduce A to the identity also transform the identity into the inverse. Okay, and in the proof, what they do is they talk about these little what are called elementary matrices. I can actually show why this works, and I'm gonna try to leave about 10 minutes in class here, so you can take a look at your orientation quiz. But let me bring up a handout that I made. Okay, and you don't have to copy this down. Okay, it's going to be in the recording here. And if you want to copy it down later, that's fine. But okay, so here is a matrix A. Here's a matrix A, 2x2 matrix. I'm doing it for a 2x2. Show that the same sequence of elementary row operations that reduces this matrix A to the 2x2 identity also reduces the 2x2 identity to the inverse matrix. Okay, that's what so this is a discussion problem. All right, so let me show you how this works. So, because you should really understand, you should appreciate, you know how the algorithm works. It'd be nice to believe in the algorithm, why it works. And I'm going to show you that. So what I have here in this first line is I take the matrix A and I do row operations to get it to the identity. So like for instance here, what I did was I took row 1 and I swapped it with row 2. Okay. Here I took -2 times row 1, added that to row 2, and put the result in row 2. And then here, okay, for this matrix, I'll maybe put it in purple, I took -1/5 times row 1, row 2, and put the result in row 2. Scalar operation. And then finally, the last step, what I did was I took -4 times row 2, added it to row 1, and put the result in row 1. Okay, so there were 4 row operations I did to finally row reduce the matrix A to show that the matrix A is row equivalent to the identity. But what you can do is you can use elementary matrices to perform the same thing. So like here I have a matrix, the matrix A, okay? And if I were to multiply the matrix A by this elementary matrix E1, and what does that elementary matrix E1 kind of look like? What does the elementary matrix E1 kind of look like? I mean, it doesn't quite look like the matrix, but it has zeros and ones in it. What other matrix has zeros and ones that you know of? The identity. That's right, Benjamin. That's right, Marvelous. So an elementary matrix is when you take the identity matrix and perform a row operation. Well, the first row operation I did was to swap rows 1 and 2. The elementary matrix E1 here is the same as taking the identity and swapping rows 1 and 2. Swapping the rows. And notice, if I multiply this elementary matrix E1, if I multiply the elementary matrix E1 times the matrix A, I'm going to get the same matrix I got here. The same matrix. So essentially, I'm doing the row operations by doing a matrix multiplication. Okay, let's look at the second elementary matrix. The second elementary matrix, E2, okay, that is equal to this matrix here. Well, if we took the identity matrix and multiplied -2 times the first row of the identity matrix and added it to the second row, we would get this E2 elementary matrix. Notice that's the same row operation that we did here. We took -2 times row 1 and added it to row 2, and so again, this E2 elementary matrix, if I take -2 times, if I take the identity matrix, multiply it by -2, no, if I take the first row of the identity matrix, multiply that by -2, and add that to the second row of the identity matrix, and then replace the second row of the identity matrix by that result, we're going to get E2. Well, that's the exact same row operation that we did here on our second step. Exact same row operation. And notice that when we take E2 and multiply it by this now, E1 times A, which is 1, 4, 2, 3. Hold on. Yeah. Wait. Yeah. If we take that E2 here, okay, that's E2. I just retyped it again and multiply it by 1, 4, 2, 3. We're gonna get 1, 4, 0, -5. 1, 4, 0, -5, and that's what we got here on the second step. Okay, do you see that? Is anybody uncomfortable with that? You might have to look at it a little bit then, you know, on your own time. But the point is, well, are there any questions so far? All right, so Haley, that's a very good question. How do you know which elementary matrix corresponds to the row operation? What I do is, the row operation that I want to do, I will do to the identity matrix, and that corresponds to the elementary matrix. So like the first row operation I did was I switched rows 1 and 2. Well, the first elementary matrix is take the identity matrix and switch rows 1 and 2. The second row operation I did was I took -2 times row 1, added it to row 2, and replaced row 2 with that result. Take the identity matrix, multiply the first row by -2, add that -2 times row 1, add that to the second row, and then replace the second row by that result, and you will get this second identity matrix, this second elementary matrix. Do you see, Haley? Does that help a little bit? Okay, excellent. And every row operation we do, right, can be represented by an elementary matrix. For the third step, for instance, we have, well, I want to be, hold on here. Yeah, the third step, the third row operation, all we did was take the second row and multiply it by -1/5 and replace the second row with that result. Well, here's here's the E3 matrix. That's the same as taking the identity and multiplying the second row of the identity by -1/5. Okay. What's a common mistake? Let's see, Francesca asks, what's a common mistake usually people do when reducing an elementary matrix that corresponds to row reduction? I don't know, Francesca. I mean, I haven't really seen too many common mistakes. I mean, this is just, the reason I'm doing this is normally when you do your row operations, you're not finding these elementary matrices. Okay, you're just doing the row operations in your mind, and then writing down row equivalent matrices, and then showing the instructions on the right. But what I'm trying to, but theoretically, it's helpful to see that it's helpful to describe the process of row reduction by matrix multiplication. And in fact, this entire row, all these 4 row operations that I did on the matrix A can be represented by pre-multiplying the matrix A by E1, E2, E3, and E4. That's what we do. Now you might wonder, why is that helpful? Because look at what we can do. This is true. The 4 sequences, the 4 row operations we did, represented by elementary matrices E1, E2, E3, and E4, that will, so multiplying the matrix A, pre-multiplying the matrix A by E1, E2, E3, and E4 will produce the identity matrix. But now what we can do is we can take the matrix equation here and multiply on the left of both sides of the matrix equation by this inverse. So the product of these 4 elementary matrices is going to be invertible, because each of the matrices themselves is invertible. And so what happens is when you take on the left side here, you're going to get on the left side, I mean, hold on here, this here, that matrix product times this matrix product gives you the identity. And so the matrix A is just equal to the inverse of the product of those elementary matrices. But that means that the inverse of that elementary matrix is the inverse of that inverse. And so A inverse is just equal to the product of those elementary matrices. Well, that means then the A inverse can be written as the product of those elementary matrices times the identity matrix. And this shows that the same sequence of elementary row operations that reduce the matrix A to the identity matrix also reduces the identity matrix to A inverse. Okay, because what are you doing here? What are you doing here? You're taking the identity matrix and you're performing these row operations on the identity matrix, and that's going to give you the inverse matrix. And so this justifies the algorithm for finding A inverse. How many think that's really pretty cool? It's a little bit theoretical, but it's not that, I mean, I just wanted to have a little example to motivate why the algorithm for finding the inverse works. How many think this? Okay, Haley thinks it's very cool. All right. Might we have a few other people? I mean, you don't have to say it's very cool, but I appreciate it. Eleanor likes it, and I made up this example for you. This example I made up for you to see it. Okay, thank you, Eleanor. Thank you, Olivia. Excellent. Are there any questions? Okay, let me stop the recording.